Today on the Perception in Action podcast, a look at perceptual learning. How does experience and practice change our ability to extract information from our environment? And how can we best facilitate this process? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. On today's episode, I want to begin a multi-part series on the topic of perceptual learning. In this first episode, I want to introduce the concept, talk about what perceptual learning is and isn't, and look at some of the mechanisms that might be involved. In the following episodes, I will get more specific to sport, digging into some of the research which has examined how athletes learn to pick up information on the sports field. To illustrate what perceptual learning is and is not, consider the task of returning a tennis serve. When first acquiring the skill, there are actually several different types of learning that can take place. First, there is declarative learning, which involves encoding factual information in memory. For example, learning the rules of tennis, such as what a double fault is, or remembering the strategy taught to you by your coach. Things like, on the second serve, when ahead in a game, I'm going to charge the net. The second type of learning is procedural, which involves putting together sequences of actions. For example, moving one's body and executing a backhand stroke. A third type of learning that can take place is the development of stimulus-response associations. For example, when I perceive a serve down the line, prepare for a backhand. So, the learner develops more extensive, rule-based and strategic knowledge of the game, develops a large repertoire of actions, and is able to link what she or he perceives to appropriate actions. But there's actually another type of learning that takes place. With practice, their perception of the flight of the ball itself will change. They will detect and distinguish features, differences, and relations in the basic sensory information that were not previously registered at all. Much in the same manner as the experienced wine taster or a chef, or a trained radiologist looking at an X-ray, or a highly skilled musician listening to a composition, the tennis player will perceive structure in their sensory environment where there was none before, and that is invisible to those that do not have the same level of experience. So, this type of learning is not just better memory, or the ability to attach a stimulus to an action, or the ability to move in a certain way. Perceptual learning is the discovery of new structure in our sensory stimulation. To understand the process of perceptual learning a bit better, let's take a step back from the tennis court and look at one of the most basic measures of visual perception there is, vernier acuity. Imagine I present on a screen two small vertical lines, one above the other. The bottom line always stays in the same location, while the top line can either be offset slightly to the left or slightly to the right. Your task, in this vernier acuity test, is to judge the direction of the offset, right or left. What is the smallest misalignment you think you would be able to detect? As is typical in vision research, let's talk about the distance in terms of degrees of visual angle. So, a separation of 1 degree would be roughly the size of your thumbnail when you hold your arm straight out at arm's length. Would you be able to detect the offset with this big of a separation? Yes, of course, that would be trivially easy. But what about a separation of 1/2 degree, or 1/4 of a degree, or 1/8 of a degree? What is the minimum offset between the two lines that you could reliably detect, aka your vernier threshold? The answer is actually unbelievable. It's not uncommon for people to have vernier thresholds of 10 arc seconds. What does that mean? Hold your thumb at arm's length, divide it into 500 vertical slices. If the lines were offset by 1 slice, we'd be able to detect the misalignment. What's even more remarkable about this ability is the apparatus we use to detect it. A Vernier threshold of 10 arc seconds is actually smaller than the size of one cone photoreceptor in our eye. So we're achieving the impossible, seeing at a higher resolution than should be achievable with our visual hardware. It's akin to hooking up a standard definition TV and getting it to project an HD image. For this reason, our Vernier acuity threshold is often called a hyperacuity. But why am I bringing this up in the context of perceptual learning? Well, think about this Vernier acuity task. There's no strategy involved. It doesn't require learning any rules or performing any actions. There are no eye movements involved, and the person can't learn to anticipate anything. It's just 2 lines on a screen. It can't get much more basic than that. Surely, if we practice this task, there is no way we could get any better at it. It must just be determined by our visual hardware. But we do get better, and by a lot. With practice, people can reduce their Vernier threshold by a factor of 6. The same is true for other basic visual judgments, like discriminating the orientation of a line or the direction of a moving object. Let me point out a few more key aspects of this type of learning. First, the type of improvements I'm talking about, in things like Vernier acuity, occur in adults. As I talked about back in episodes 38 and 39, children have an incredible ability to essentially rewire their brain in response to the stimulation they receive, and show rapid improvements in perceptual abilities. Studies of perceptual learning show that even in adults, perceptual abilities can be sharpened with extensive exposure or training. Second, perceptual learning is not just learning to look in the right place. As I discussed way back in episode 3, developing effective visual search strategies, for example, increasing one's quiet eye duration, does seem to be related to skill acquisition in sport. But even when we take eye movements completely out of the equation, by presenting a person with a static image, or having presentations so brief that it's impossible to move one's eyes, perceptual learning still occurs. In other words, they get better at perceiving what is there, no matter how their eyes get there. Third, perceptual learning is not just learning to focus one's attention on the right thing. Some interesting recent studies have shown that you can actually get completely passive perceptual learning by presenting peripheral stimuli that are completely irrelevant to the task a person is performing and therefore are not attended. So, for example, if you have a person make judgments about letters presented in the center of a screen, while at the same time presenting patterns of motion in their periphery, which they are told to ignore, their motion perception will actually improve with practice. These findings are consistent with the co-activation theory first proposed by Donald Hebb, which argues that learning and neuroplasticity can occur simply on the basis of things being presented in synchrony. This research also highlights the fact that perceptual learning does not necessarily require changes in conscious processes. Fourth, perceptual learning is not just taking advantage of situational probabilities or an opponent's tendencies like I talked about back in episode 3. Nor can it be described using the Bayesian models which incorporate prior probabilities like I talked about back in episode 34b. When we look at any type of perceptual task, we can separate 2 different types of effects that occur with practice: changes in sensitivity and changes in bias. Anticipating a cross-court serve when our opponent faults on the first serve, because we know from analyzing their previous game footage that they always do this, is an example of a change in our bias. We are changing the likelihood of perceiving one outcome over another due to the statistics of our environment. This type of ability does not reflect a change in sensitivity. That is, it does not mean that we're actually better at perceiving the flight of the ball itself. The key point I want to make is perceptual learning actually does involve changes in sensitivity, not just changes in bias. This can be shown in a few different ways. First, obviously, we could take out all situational probabilities and make events completely random, which is what is done in most basic laboratory experiments, like the ones I described which measure Vernier acuity and motion discrimination thresholds. In these stimuli, there are no regularities or probabilities to take advantage of. The direction of offset, or of motion, is chosen randomly on every trial. So it's impossible to improve one's performance by changing bias in this situation. Another way of separating bias and sensitivity is to use a technique called signal detection theory. As an example, let me tell you about a baseball study I published back in 2010. In this study, I was interested in understanding how batters decide whether or not to start their swing based on the angle at which a ball is launched when it leaves the pitcher's hand. In general, the launch angle could give the batter some useful information. For example, when this launch angle is very big, it's likely the ball will cross the plate above the strike zone. While if this launch angle is very small, it's likely the pitch will cross the plate below the zone. So in both these cases, the batter should choose not to swing. But there is a problem. The relationship between launch angle and the height the ball crosses the plate also depends on the pitch speed. So for example, a fastball thrown with a relatively small launch angle may hit the bottom of the zone, while a changeup thrown at the same angle but at a lower velocity may not, because it will be affected more by gravity. So, how do batters make this decision, and how does it change with learning? To investigate this, I presented experienced college players and lesser skilled recreational batters with a range of different launch angles and pitch speeds in my batting simulation, and looked at when they did and didn't initiate their swing. I then used signal detection theory to separate sensitivity from bias. In this case, the bias I was expecting was a tendency related to baseball umpires, who tend to call more low strikes than high strikes. In signal detection theory, you divide the outcomes of your performance into 4 possibilities: hits, misses, false alarms, and correct rejections. In my batting example, a hit was not when they made contact with the ball, but was rather when they initiated a swing for a ball that was going to cross the plate in the strike zone, which is of course a good thing. The other good outcome that can happen is a correct rejection. In my case, this is when they did not swing at a ball that ended up out of the strike zone. The 2 bad performance outcomes are then false alarms, which is swinging at a ball out of the strike zone, and a miss, which is not swinging at a ball that was in the strike zone. What did I find? The expert batters had both significantly higher sensitivity and a different bias than the lesser skilled players. In terms of bias, as I predicted, expert batters initiated more swings at low pitches as compared to the less experienced batters, a practice that would serve them well in actual gameplay due to the umpiring tendencies. And indeed, there was a significant correlation between this bias I calculated in the study and their batting average in actual gameplay. But what about sensitivity? In signal detection theory, this is calculated by subtracting the proportion of false alarms from the proportion of hits, which gives you a value called D prime. When I did this, sure enough, the expert batters had higher D prime values, indicating greater sensitivity. This suggests that perceptual learning had occurred through practice, such that they were just better able to perceive the flight of the ball as compared to players with less experience. A couple final points before I look at some of the proposed underlying mechanisms for perceptual learning. First, perceptual learning is obviously highly task-specific. It involves improving one's ability to detect structure in the pattern of stimulation that is relevant to the task being performed. It's not just a general improvement in one's ability to perceive the world. When we're performing a specific skill, clearly not all properties of the outside world are relevant. Filtering out information that is irrelevant, while at the same time discovering the structure that is what is key, not just getting better at perceiving all of it. The level of task specificity in perceptual learning can actually be ridiculously extreme. For some tasks, like learning to judge the orientation of a line, it's been shown that the improvements that occur with practice do not transfer when the line is moved to a slightly different location on the screen, or when training occurs with one eye and then is tested in the other, what is called intraocular transfer. Also, as I discussed back in episode 19C, you do not get perceptual learning when you train with stimuli that are well above a person's perceptual threshold. But despite all this, there are actually cases where you get robust transfer of perceptual learning, which I'll be discussing next time. Finally, I'd like to emphasize a connection many of you may be thinking about already. That is between perceptual learning and perceptual motor development. In particular, Eleanor and James Gibson's conception of development. As I discussed back in episodes 38 and 39, the traditional approach to understanding how our perception improves as we age is what we might call an enrichment view. That is, we improve in our ability to see our world by learning to add meaning to the previous meaningless sensory stimulation we receive. We do this through making associations and using our past experiences. In this view, perception is characterized as a process of construction, hypothesis testing, or making inferences, such that the more learning occurs, the less important our raw sensory perception becomes, because what we perceive becomes more and more reliant on previously acquired information. The Gibsons argued that the truth of perceptual development may actually be quite the opposite. Experience might make perceivers better at using currently available information. With practice, perception might become more, not less, in correspondence with the given information. They called this view of development differentiation, and this is exactly the type of process we're referring to in perceptual learning. Okay, so we talked about what it is and what it isn't. Now the $64 million question. Why does it occur? Why do we learn to perceive the world better with practice? If it's not memory, attention, anticipation, eye movements, use of situational probabilities, what is it? There have been basically three hypotheses put forth to explain this phenomenon. The first, receptive field modification, is the idea that there may be a change in the receptive fields of the neurons that are encoding the stimulation. A receptive field is essentially the range of features that an individual neuron responds to. So, for example, we have neurons in our brain that only become active when objects move towards us, and then a separate set of neurons that only respond when an object moves away from us. Receptive field modification is the idea that with practice, our neurons begin to reorganize to become more appropriate for the stimuli we're experiencing. So, for example, if we play a sport which involves lots of objects coming at us at slightly different angles, like tennis, instead of our brain just having lots of towards motion neurons, they begin to differentiate and become more specialized. So with learning, we develop a 20 degree to the left movement neuron and a 20 degree to the right neuron, instead of just all ones that respond to anything that is approaching. Other changes that could occur might be in the area of visual space the neurons are sensitive to. If the stimulation is always occurring in the same location, the size of a neuron's receptive field may be reduced to focus more on this area. Also, in some cases, neurons that did not respond to this type of stimulation at all may be recruited. So essentially, with this hypothesis, we're putting more brain power into the job. The second common explanation for perceptual learning is selective reweighting, which argues that instead of individual neurons changing their properties, learning affects the way neural signals are combined. For example, learning might be explained in terms of the discovery of which of our neural analyzers best perform a classification, and then increasing the weight on such analyzers. These first two explanations were really proposed for perceptual learning using very simple tasks, like the Vernier acuity and orientation discrimination tasks I discussed. The final theory is a better fit for more complex tasks, like the ones that occur in most sports. It is the idea that with practice, we become able to detect higher order sources of information in the scene that we did not notice before. Think of a TV detective looking at the layout of crime locations, suddenly noticing that there's a pattern there. An interesting issue with this hypothesis is whether these higher order variables have to be constructed from the perception of lower order ones, kind of like in a chunking process, or whether they were there all along and just abruptly become perceptible. I'll be considering this question and evidence for all the different hypotheses in a future episode. So, to sum up, we've seen today that with practice in any domain, we become attuned to the features and structural relations that are relevant to the task we're performing. And over time, we come to extract these with increasing selectivity and increasing fluency. This occurs separate from other changes related to cognition, attention, and memory. Perceptual learning is a truly remarkable ability, and it serves as a crucial foundation of human expertise. In my next episode, I'll dig a bit deeper into this topic, looking at how this occurs specifically in sport and how we might better facilitate it. You can contact me via email at robgray@asu.edu or on Twitter at ShakyWeights. And remember, you can find everything you ever wanted to know about this podcast at perceptionaction.com. This is Rob Gray from ASU. Cheers for now.